Welcome to Fun Facts Online. In the grand tapestry of scientific discovery, every so often, a thread emerges that is so revolutionary it reweaves our understanding of what is possible. We are at the precipice of such a moment. The protagonist of this story is a molecule we all know, the very blueprint of life itself, DNA. But in this narrative, DNA is not merely a passive carrier of genetic information. It is an active, programmable construction material, a nanoscale architect building the materials of tomorrow. Researchers have unlocked a method to command DNA strands to build intricate, layered nanostructures known as Moiré Superlattices. This is not just an incremental advance, it is a leap into a new era of material design. To fully appreciate this, we must first shrink our perspective to the nanoscale. A nanometer is a billionth of a meter. A single human hair is about 80,000 nanometers wide. At this level, the familiar rules of classical physics give way to the strange principles of quantum mechanics. Nanotechnology is the art and science of manipulating matter at this scale. The properties of materials can change dramatically. A substance that is opaque might become transparent. An insulator might become a conductor. The challenge has always been in the how. The traditional approach, known as top-down fabrication, is like sculpting. You start with a large block of material and carve away what you don't want. This is how computer chips are made. But as we try to create smaller and more intricate structures, our carving tools become blunt. The process becomes complex and expensive. This is where bottom-up assembly comes in. Instead of carving, you build structures molecule by molecule, like using Lego bricks. The ultimate form of this is self-assembly, where the building blocks are programmed to build themselves. This is nature's perfected method, and it is the inspiration for this revolutionary new work. For most of its history, DNA has been understood as the molecule carrying our genetic instructions. But in recent decades, scientists have begun to see DNA as a remarkable building material. The properties that make DNA so good at storing genetic information also make it an excellent candidate for building nanoscale structures. The key lies in the highly specific and predictable way its strands interact. The nucleotide base adenine always pairs with thymine, and guanine always pairs with cytosine. This is like a molecular glue with a very specific set of rules. By synthesizing single strands of DNA with specific sequences, scientists can program them to bind to other strands in a predetermined way. The DNA double helix itself is also ideal for nanoscale construction, with a diameter of about 2 nanometers and a predictable twist. It's regular, precise, and thanks to molecular biology, we have a vast toolkit for manipulating it. This ability to program molecules to self-assemble is the foundation upon which the future of advanced materials is now being built. Among the various techniques in the DNA nanotechnology toolbox, one stands out for its power and versatility: DNA origami. The name is a fitting analogy. Just as the Japanese art creates complex shapes by folding a single sheet of paper, DNA origami creates complex nanostructures by folding a single, long strand of DNA. The process begins with this long scaffold strand, often the genomic DNA from a virus, which is thousands of nucleotides long. This long strand is then folded into a desired shape by hundreds of short, synthetic DNA strands called staple strands. Each staple is designed to bind to 2 or more specific regions of the scaffold. In doing so, they act like molecular clips, pulling different parts of the scaffold together and holding them in place. The self-assembly process is remarkably simple in practice. The scaffold and staple strands are mixed in a solution, heated to straighten them out, and then slowly cooled. As the temperature drops, the staples bind to their programmed spots on the scaffold, and the entire structure quickly snaps into its predetermined shape. The power of DNA origami lies in its addressability. The scaffold is like a molecular breadboard. and scientists can control the precise placement of every component. This allows for the creation of incredibly complex shapes, from smiley faces and nanoscale maps to intricate gears and boxes with lids that open and close. This tool, with its unprecedented precision, sets the stage for the next leap forward, the self-assembly of Moiré superlattices. The term Moiré pattern describes a familiar visual phenomenon. It's the interference pattern created when two similar but slightly offset grids are overlaid, like looking through two layers of a fine meshed screen. In materials science, Moiré superlattices are created when two atomically thin 2D materials, like graphene, are stacked on top of each other with a slight twist angle. When this happens, something extraordinary occurs. The slight misalignment creates a new, larger periodic pattern. This superlattice acts as a potential field that can dramatically alter the behavior of electrons in the material. Crucially, the properties of this system are highly dependent on the twist angle. By simply changing the angle, scientists can tune the material's electronic and optical properties in ways previously unimaginable. The most famous example came in 2018 with magic angle twisted bilayer graphene. Researchers found that when two sheets of graphene are twisted by about 1.1 degrees, the material exhibits a range of fascinating quantum phenomena, including unconventional superconductivity. This discovery sparked a frenzy of research into what's now called twistronics. The potential applications are vast, from new types of transistors to materials with tunable light absorption for lasers and detectors. The key to unlocking all this potential lies in precisely controlling that twist angle. And this is where the old way of doing things falls short. The conventional method for fabricating Moiré superlattices is a top-down approach, a form of nanoscale cut and paste. It typically involves mechanically peeling off a single atomic layer of a material with adhesive tape, transferring it to a substrate, then picking up a second layer and carefully placing it on top of the first with a precise twist. This entire process is incredibly delicate, laborious, and prone to error. Achieving the desired twist angle is a major hurdle. Small deviations can dramatically alter the properties. The process also introduces strain, wrinkles, and bubbles between the layers, which can ruin the device. Furthermore, this method is not scalable. It's a time-consuming, one-at-a-time process fine for a lab, but impractical for manufacturing. The field desperately needed a new approach, one that could create these structures with high precision, high yield, and greater design flexibility. Now, in a landmark development, researchers have pioneered a revolutionary bottom-up approach using the programmability of DNA. This new paradigm, from a team at the University of Stuttgart and the Max Planck Institute, leverages DNA self-assembly to build these intricate nanostructures with unprecedented precision. The method combines two DNA nanotechnology techniques, DNA origami and single-stranded tile assembly. The process starts with a DNA origami seed. This seed is a precisely engineered blueprint that encodes the geometric parameters of the final Moiré superlattice. The twist angle, the layer spacing, and the lattice symmetry are all programmed into the molecular design of this seed. This seed then acts as a template. Its surface is decorated with capture strands of DNA, which act as molecular hooks. These hooks are designed to bind to specific single-stranded DNA tiles, or SSTs, which are the building blocks that will form the superlattice layers. When the DNA origami seeds and the SSTs are mixed in a solution, the capture strands on the seed grab the tiles, directing their assembly into a precisely ordered first layer. A second set of capture strands on the seed then directs the assembly of a second layer on top of the first. The genius is that the seed's design ensures the second layer is assembled with a specific, pre-programmed twist angle relative to the first. The result is the spontaneous formation of a perfectly twisted bilayer DNA Moiré superlattice. This method offers a level of control unattainable with mechanical stacking. The twist angle is a direct consequence of programmed molecular interactions, allowing for highly uniform and predictable properties, with deviations of less than 2 degrees. Even more remarkably, this approach allows for gradient Moiré superlattices, where the twist angle varies continuously across the structure. This bottom-up, self-assembly approach is a fundamental shift in how we build. The ability to construct Moiré superlattices with this level of precision is a gateway to a new world of technology. One of the most exciting frontiers is spintronics. Conventional electronics use the charge of electrons. Spintronics aims to also use their spin. Spintronic devices promise to be smaller, faster, and more energy efficient. Moiré superlattices can act as a spin filter, and the DNA-based fabrication method is perfectly suited for this. Researchers can use the DNA origami seed to not only control the twist angle, but also to precisely position magnetic nanoparticles within the structure. This could lead to a new class of highly programmable spintronic devices. The demonstration of gradient Moiré superlattices also opens up fascinating possibilities in optics. These structures can function as gradient index materials, which have a refractive index that varies with position, like the lens of the human eye. By creating DNA-assembled superlattices with a controlled gradient, scientists can design materials that steer light and even sound waves along specific paths. This could lead to flat lenses, new types of waveguides, and even optical cloaking devices. Beyond their own properties, these DNA Moiré superlattices can serve as highly precise scaffolds for assembling other nanoscale components. Researchers can attach fluorescent molecules for biosensors, metallic nanoparticles, or semiconductor quantum dots to build more efficient LEDs or even components for quantum computers. The possibilities are truly vast. We are not just mimicking quantum materials. We are expanding the design space to build new types of structured matter from the bottom up. Of course, every revolutionary technology faces hurdles. One of the most significant is the scalability and cost of DNA synthesis. While the price has dropped, producing the large quantities needed for commercial applications is a major challenge. Another is stability. DNA is a biological molecule and can be degraded by enzymes or high temperatures. For applications in electronics, long-term durability is a critical concern. Scientists are working on coating the DNA with protective layers or even chemically transforming the DNA scaffold into a more durable material, like silica, after assembly is complete. Finally, there's the challenge of integration. We need methods to place these nanostructures onto surfaces like silicon wafers and make electrical and optical connections to them. This interface between the bottom-up world of self-assembly and the top-down world of conventional fabrication is a major area of research. In conclusion, we stand at a remarkable juncture. The elegant simplicity of DNA's base pairing rules has been harnessed to solve one of the most complex challenges in modern material science. This convergence of biology and physics has given birth to a technology with truly transformative potential. The ability to program matter from the bottom up, to dictate the flow of electrons and photons with molecular precision, is a power humanity is only just beginning to grasp. The self-assembly of DNA Moiré superlattices is more than a new fabrication technique. It is a new way of thinking about building the world around us. As we learn to speak this molecular language of creation, we will unlock the ability to design materials with properties we can currently only dream of. The threads of DNA are weaving the fabric of a new technological age, 1 nanometer at a time.